There are places on this planet that make you question everything you've been taught. Not because they seem impossible, but because they shouldn't be possible at all. The Great Pyramid of Giza rises from the Egyptian desert, like a geometric perfection carved from stone, 6.5 million tons of it, stacked with such precision that you cannot slide a human hair between the blocks. Think about that for a moment. Not a modern machine precision, not a computer-guided laser. Ancient hands, ancient tools. And yet the fit is so exact that archaeologists today still puzzle over how the joints achieve such tightness, without mortar, without any binding agent whatsoever. On the other side of the world, in the high valleys of Bolivia, sits Puma Punku. The stones here tell a different story, and yet somehow the same one. Angles so precise they appear almost mechanical, cut with such accuracy that you'd swear modern equipment carved them. The blocks interlock in 3 dimensions, fitting together like a 3-dimensional puzzle with tolerances that would make a modern engineer pause and recalculate. Then there's Baalbek in Lebanon, where stones weighing over 800 tons, roughly the weight of a jumbo jet, sit positioned with surgical accuracy on a platform built thousands of years before we supposedly developed the machinery to move such weights. Each of these sites exists independently, separated by continents and centuries. Yet they share something unsettling. They all contain a level of precision that doesn't fit comfortably into the story we've been told. For nearly 200 years, archaeologists explained these wonders away with a narrative that felt safe and logical. Manpower, they said, determination, primitive tools, and incredible patience. The idea was almost romantic. Ancient peoples, through sheer will and organization, moved mountains and built monuments that would outlast empires. And there's truth in that narrative. We shouldn't dismiss the ingenuity or determination of ancient peoples. But as we dig deeper into the actual evidence, as we examine what remains at these sites, contradictions begin to surface, like cracks in a carefully maintained facade. The precision doesn't just exist, it increases the further back we look, which shouldn't happen if construction methods were developing and improving over time. The construction timelines compress impossibly when you do the actual mathematics of moving stone at the scale we're discussing. The tools needed to achieve this work in the quantities required would leave traces, debris fields, broken implements, and yet these traces are mysteriously scarce or absent entirely. Something doesn't align. Something in our understanding of how these monuments were built has a fundamental problem. What's remarkable isn't that a single civilization achieved something impressive. Human beings are capable of remarkable things. What's remarkable is that isolated civilizations completely cut off from one another, separated by oceans and millennia, seem to possess similar engineering principles, similar astronomical knowledge, and similar architectural approaches. It's as if they were reading from the same instruction manual, or as if they independently discovered the same universal truths. Either possibility suggests something profound about ancient human capability that contradicts what mainstream archaeology has been comfortable asserting for generations. This isn't about dismissing modern science or embracing fringe theories. It's about acknowledging that when evidence accumulates in a consistent direction, when contradictions mount, when the official explanation requires us to ignore increasingly obvious problems, maybe it's time to ask different questions. Not to abandon rigorous thinking, but to extend it further, to look at what we've already decided is settled, and ask, are we certain about this? The answer might surprise us. But first, we need to understand how we arrived at our current certainty in the first place. The story of modern archaeology begins with confidence. In the 19th century, as European powers expanded across the globe, as the Industrial Revolution transformed what humans could build and move and control, Western science developed a particular way of seeing the world. Everything that came before the modern era was measured against modern capability. If we built something with machines, the logic went, then surely everything that came before must have been built with muscle and determination. This wasn't a scientific deduction that emerged from careful investigation. It was an assumption, nearly unconscious, wrapped in the certainty of an age that believed itself superior to everything that had preceded it. When formal archaeology emerged as a discipline in this context, it inherited that assumption like a genetic trait. Scholars approached ancient sites with frameworks already constructed. They looked for evidence that fit their expectations. When they found something that contradicted those expectations, a curious thing happened. Rather than revising the framework, they revised the interpretation. Evidence became flexible when facts became inconvenient. This process repeated itself across decades and centuries, until the framework calcified into something that looked like objective truth. The problem compounds itself through institutional reinforcement. Universities built departments on these frameworks. Careers were built. Funding flowed to expeditions that produced confirming evidence. Publications promoted work that fit the established paradigm. Journals rejected papers that challenged it. Any archaeologist who suggested substantially different interpretations of how ancient monuments were constructed risked something precious: professional standing. The scientific method, which should encourage questioning and hypothesis testing, actually became a guardian of orthodoxy, not through malice or conspiracy, but through the simple mechanics of how institutions protect themselves. This isn't unique to archaeology. Throughout the history of science, paradigms become entrenched. Scientists invest their professional identities in particular frameworks. These frameworks generate research questions, funding priorities, and acceptable conclusions. Evidence that threatens the paradigm is treated differently than evidence that confirms it. Studies that corroborate established thinking receive media attention and funding. Studies that challenge it are minimized, critiqued exhaustively, or simply ignored. The scientific method exists to prevent this bias. But the scientific method is implemented by humans working within institutions, and humans are susceptible to confirmation bias, career preservation, and institutional pressure. What makes this particularly significant for archaeology is that ancient sites don't regenerate. Once excavated improperly, once evidence is disturbed or lost, it's gone forever. Early archaeologists, working with less sophisticated techniques and different priorities than modern specialists would employ, sometimes excavated without the careful documentation we'd expect today. Evidence was collected, catalogued inadequately, or lost. The knowledge about how excavations proceeded exists only in fragmentary records. If those early excavations were conducted with assumptions that shaped what was deemed important to record and what could be dismissed, the bias became embedded in the historical record itself. Subsequent archaeologists, building on those early excavations, inherited not just the physical evidence, but the interpretive framework that shaped how that evidence had been evaluated. Consider how this worked in practice. When construction techniques couldn't easily be explained through available tools, rather than questioning the assumptions about available tools, scholars simply asserted that ingenuity and determination overcame technological limitations. When precision exceeded what seemed possible with primitive methods, this was accepted as remarkable, but not impossible. When evidence of construction methods was absent, this was simply treated as inevitable loss, rather than suggesting that different methods entirely were employed. Each interpretive choice seemed reasonable in isolation. But accumulated across decades and centuries, these choices formed a coherent narrative that became increasingly difficult to question, because the entire institutional structure depended on it. What's important to understand is that this isn't the fault of individual archaeologists. Most are genuinely committed to understanding the past accurately. They're following frameworks they inherited, asking questions within parameters they didn't establish, and working within institutional structures that reward confirmation and discourage revision. The problem is systemic, not personal. And systemic problems require acknowledging the system itself before they can be addressed. This recognition doesn't require abandoning archaeology or dismissing scientific expertise. It requires understanding that expertise operates within paradigms, and paradigms can outlive their usefulness. Before we examine specific mysteries, we need to establish the scale of what we're investigating. This isn't about one peculiar site or one anomalous structure. Across the planet, across different eras, across supposedly isolated civilizations, we find consistent patterns of engineering sophistication. From Egypt to Peru to Cambodia to Turkey, we encounter the same hallmarks: massive stone blocks fitted with extraordinary precision, astronomical alignments of uncanny accuracy, water management systems of stunning sophistication, and geometric relationships that embed mathematical knowledge. Consider what this means. The precision required in Egyptian temples appears again in pre-Incan structures on the other side of the world. The astronomical knowledge demonstrated in Egyptian sites appears in Mayan records, separated by centuries and continents. The architectural proportions embedding mathematical relationships show up across cultures that had no documented contact. These patterns suggest either that knowledge was transmitted across cultures in ways our historical narratives don't fully account for, or that humans independently discovered similar principles when reaching comparable technological sophistication. What makes this particularly striking is what's absent from the archaeological record. When we examine construction sites where we claim primitive methods built monuments, we find remarkably little evidence of those methods actually being employed. The debris fields we'd expect are minimal. The tool caches are scarce. The worker camps that supposedly housed hundreds of thousands leave minimal archaeological signature. The limestone blocks used at the Great Pyramid came from quarries miles away, yet we find relatively little evidence of large-scale quarrying operations. The transportation methods that supposedly moved these blocks leave surprisingly little trace. This isn't proof of anything. Absence of evidence isn't necessarily evidence of absence. Ancient sites have been heavily disturbed, looted, and modified over millennia. Much evidence has simply been lost to time. But the consistent pattern across multiple sites, across multiple civilizations, of missing evidence supporting the conventional methodology, while physical evidence shows undeniable sophistication, creates a coherent pattern worth examining seriously. The precision these ancient peoples achieved isn't just remarkable in isolation. It's remarkable because achieving such precision without modern measurement tools requires either developing sophisticated measurement technology or possessing knowledge systems fundamentally different from what we've assumed existed. When you see precision replicated across cultures and centuries, you're not observing accidents or isolated achievements. You're observing systematic capability, and systematic capability suggests systematic knowledge. The question that emerges isn't whether ancients were capable, the evidence proves they were. The question becomes, what enabled that capability, and why don't we understand it? The Great Pyramid of Giza has been studied more extensively than perhaps any human construction in history. Thousands of scholarly papers examine its dimensions, its internal structure, its astronomical alignments, its mathematical properties. And yet, for all that study, fundamental questions about how it was actually constructed remain deeply contentious. Let's examine the mathematics. Because mathematics doesn't lie, and it doesn't depend on interpretation or belief. The structure contains approximately 2.3 million stone blocks. That number isn't approximate in the sense of being uncertain. The pyramid has been examined extensively. We know roughly how many stones comprise it. The average weight of these blocks is 2.5 tons. Some weigh as little as a ton, some weigh 15 tons or more. Now, the official timeline for construction places the pyramid's building during the reign of Pharaoh Khufu, a reign spanning roughly 20 years. Do the mathematics with me. 2.3 million blocks divided by 20 years equals 115,000 blocks per year. Divided by 365 days, that's approximately 315 blocks per day. Every day. For 20 consecutive years. No breaks for religious festivals, floods, or the practical limitations of moving massive weights in the Egyptian heat. This isn't speculative. This is what the conventional timeline requires. Now consider what actually moving and placing a 300-ton block per day entails. You need to quarry it. The nearest quarry is miles away. You need to transport it across desert sand. You need to position it precisely, because the pyramid stones don't just sit loosely, they fit together with extraordinary precision. The official explanation involves copper chisels and wooden sledges. Copper chisels. The metal is soft enough that you could nearly dent it with moderate force. Working copper, even in its finest form, against granite requires accepting a level of patience and inefficiency that stretches credibility when multiplied across millions of blocks. The workforce required to accomplish this is equally staggering. Historical records and archaeological estimates suggest an army of 100,000 workers or more would be needed. For 2 decades, housing that many people in ancient Egypt requires infrastructure we don't find archaeological evidence of. Feeding them requires agricultural production that would strain the system. Medical care for injuries on that scale would be unprecedented. Yet we find no credible evidence of worker camps at that scale. No administrative records documenting the logistics. No burial grounds showing the massive mortality that would result from that many people working in extreme conditions. Some scholars propose rotating workforces of smaller size, with groups of workers spending limited time on the project. This creates different problems. Training specialized workers to precise standards takes time. Rotation would mean constant retraining, constant adjustment of workforce composition, constant loss of expertise. The efficiency would be catastrophic compared to maintaining a permanent, trained workforce. Yet the evidence simply doesn't support either scenario adequately. What exists at Giza are marked stones bearing what appear to be workers' marks or gang signs. These marks are real, they exist, but they're far too sparse to account for the majority of blocks comprising the pyramid. We're talking about marks on perhaps a fraction of 1% of the stones. If the entire workforce was quarrying and moving blocks, we'd expect far more extensive marking systems, more visible organization, and labor coordination. The marks we find suggest something different. A smaller, more specialized workforce, possibly employed for specific tasks, rather than the comprehensive construction enterprise the conventional timeline requires. The internal passages and chambers of the pyramid showcase an additional level of complexity. These aren't random tunnels. They align to specific stars. The angles are precise. The relationships between chambers encode mathematical knowledge. Creating this internal complexity, while simultaneously building the massive external structure, would require architectural planning so sophisticated, construction so coordinated, and measurement so precise that the primitive tools and manpower explanation becomes less an explanation and more an act of faith. What we're left with is a structure that undeniably exists, that contains undeniable sophistication, but whose construction through conventional methods remains mathematically and logistically problematic. This doesn't prove anything exotic. It simply acknowledges that the standard explanation, repeated with absolute certainty, contains internal contradictions when examined rigorously. The gap between what the conventional narrative requires and what evidence supports remains uncomfortable and unresolved. If we step back and acknowledge that conventional methods may not fully explain the pyramid's construction, what alternative frameworks become plausible? This requires asking what capabilities ancient Egyptians actually possessed, not what we assume they lacked. The Egyptians understood water. Their entire civilization depended on water management. They built canals, managed flows, created systems that functioned reliably for centuries. They understood leverage and mechanical advantage. We find evidence of these principles applied throughout their civilization. They understood precision measurement. The temple alignments couldn't exist without it. They understood mathematics at a level we're still discovering through careful analysis of their surviving records. If you combine water management, leverage, mechanical advantage, and precision measurement, what technologies become theoretically possible? Hydraulic systems capable of moving massive weights, mechanical systems using counterbalance and mechanical advantage to position stones, measurement systems enabling the precision we observe. These aren't speculative technologies we invented. They're applications of principles the Egyptians demonstrably possessed. Consider water pressure as a tool. Recent experimental archaeology has shown that water, when applied through carefully engineered systems, can create tremendous force. If ancient engineers understood this principle and developed systems to apply it, moving massive stones becomes less impossible. The Egyptian texts that reference water in construction contexts, often dismissed as purely ceremonial or religious, might contain clues about actual techniques. Unfortunately, mainstream archaeology hasn't prioritized investigating this avenue systematically. The focus has remained on muscle and tools rather than hydraulic engineering. Temporary structures represent another possibility. Perhaps ramps, platforms, or systems existed that were disassembled and reused, leaving minimal archaeological trace. We find evidence of sophisticated wooden construction in ancient Egypt, yet we don't excavate extensively for wooden post holes and traces of wooden structures that might have been central to construction, but left few permanent marks. If the construction methods deliberately minimized permanent trace, or if such traces have been lost through millennia of erosion and human activity, conventional archaeology might miss them entirely. Sound and vibration present another avenue less explored. Various ancient structures exhibit acoustic properties that seem intentional rather than accidental. Certain chambers in the pyramid create specific resonance effects. If ancient peoples understood that specific frequencies affect material behavior, causing stone to become more workable, or even facilitating positioning, the implications are significant. Modern researchers have demonstrated that ultrasonic vibrations can dramatically reduce the friction between surfaces. If applied to massive stones, this could revolutionize how they're moved. Did ancients discover this principle? We don't have definitive evidence, but neither do we have evidence they didn't. What's crucial here is methodological rigor. We shouldn't accept speculative alternatives without evidence, but we should investigate them with the same seriousness we apply to conventional methods. Currently, mainstream archaeology doesn't seriously investigate water-based construction methods, acoustic effects, or sophisticated temporary structures at Giza. These aren't studied because the paradigm doesn't accommodate them, yet evidence supporting conventional methods is equally sparse. We have contradictions in one direction and uninvestigated possibilities in another. Some experimental archaeology has tested alternative methods with varying results. When researchers have attempted to move massive stones using period-appropriate tools and manpower, the results are mixed. Some experiments succeed in moving smaller blocks short distances. Scaling these results to the millions of blocks and the pyramid's scale requires extrapolation far exceeding what the experiments actually demonstrate. Other experiments have failed entirely, unable to achieve the precision or speed required by the conventional timeline. This doesn't prove alternatives are correct, but it demonstrates that conventional methods are similarly difficult to definitively verify. The honest assessment is that we don't fully understand how the pyramid was constructed. Multiple frameworks are consistent with some evidence, none are perfect. This is where science should thrive, acknowledging uncertainty while investigating possibilities rigorously. Instead, conventional narrative maintains certainty while investigation stagnates. The pyramid stands as a monument not just to ancient capability, but to the limits of our understanding and the gaps in our scientific imagination. Precision serves as a marker of capability and intention. When something is built with precision, it requires either extremely sophisticated tools or an exceptionally effective methodology, or genuine understanding of the principles enabling that precision. The Great Pyramid's base deviates by mere inches across a perimeter exceeding 750 feet. Achieve this with modern surveying instruments, and you've accomplished something noteworthy. Achieve this without those instruments, and you've demonstrated capability that demands explanation. Pumapunku's stone blocks fit together so tightly that constructing a modern structure with similar precision would require computer-assisted design and laser measurement. The angles are so exact that variations fall within fractions of a degree across blocks that weigh many tons. The Baalbek platform contains blocks positioned with such accuracy that despite 2,000 years of earthquakes, the platform remains level. Precision at this scale, replicated across multiple sites and cultures, suggests not accidents or lucky coincidence, but systematic methodology. What's particularly striking is that achieving precision at this scale without modern measurement tools is extremely difficult. Modern stonemasons, given copper chisels and wooden mallets, the tools archaeologists claim were used, and asked to recreate ancient precision, consistently fail to achieve results matching what we observe. They can create acceptable structures, but they cannot replicate the precision of the ancient sites. This gap between claimed methodology and observed results is itself evidence suggesting something is missing from our understanding. Some researchers have proposed sophisticated measurement systems using basic principles, sighting lines, water levels, geometric relationships. These systems could theoretically achieve high precision if applied skillfully and repeatedly. The evidence doesn't contradict this possibility. But neither does the evidence suggest how such systems would have been developed, deployed, and maintained across the scale that construction at sites like Giza required. Theories exist. Evidence supporting them is limited. What we do know is that precision requires intention. You don't achieve half-inch accuracy across hundreds of feet accidentally. You don't create angles matching laser precision with casual effort. Precision indicates serious engineering, careful planning, and sophisticated understanding of geometry and measurement. When precision appears across multiple civilizations, across centuries, across supposedly isolated cultures, it indicates something even more significant. Either repeated independent discovery of similar principles, or knowledge transmission we don't fully understand. The precision paradox creates a logical puzzle. Achieving this precision requires sophisticated capability. The conventional explanation attributes this capability to muscle and primitive tools. But the tools available to ancients, as tested through experimental archaeology, cannot reliably produce this precision. This creates a contradiction. We observe precision. We claim muscle and tools created it. But muscle and tools, when tested, cannot produce equivalent results. Something in this chain doesn't connect. The honest response is to acknowledge this gap and investigate it, not by dismissing either the precision or the possibility of ancient sophistication, but by asking genuinely, what would enable this precision? What tools, what methods, what knowledge systems would be required? And do we have evidence of those capabilities existing? This question doesn't demand we accept any particular answer. It demands we stop pretending the gap doesn't exist. The precision is real. The explanation is incomplete. Rigorous investigation must address both. Humanity has always looked upward. Every culture has noticed the stars, developed explanations for their movements, created stories around constellations. This is universal enough that we rarely question it. But what if some ancient cultures possessed astronomical knowledge exceeding what naked eye observation could provide? What if they knew things about the heavens that shouldn't have been knowable without telescopes? In the Egyptian desert, at a place called Nabta Playa, archaeologists discovered megaliths aligned to astronomical points with uncanny precision. The site dates to approximately 6,500 years before the Common Era. The alignment targets Orion's belt, specifically 3 stars in that system, positioned with astronomical accuracy that rivals modern instruments. This isn't approximate. This isn't interpretation of accidentally aligned stones. The alignment is so specific that it could not occur by chance or simple observation. It required systematic astronomical knowledge maintained across generations, precise measurement, and intentional construction toward a specific astronomical goal. How is this possible 6,500 years ago? The conventional answer is that early humans were skilled naked-eye observers. They watched the stars carefully, noted patterns, developed systems for tracking movements. Over generations, this knowledge accumulated. But this explanation encounters a serious problem. The precision of the Nabta Playa alignment exceeds what we'd expect from naked-eye observation alone. The margin of error in naked-eye astronomy is significantly larger than what we see demonstrated here. The alignment is too exact. Consider another example from West Africa. The Dogon people of Mali possess detailed knowledge of the star system Sirius. Specifically, they describe Sirius B, a companion star to the main star Sirius. Sirius B is not visible to the naked eye. You cannot see it without a telescope. Yet the Dogon describe its orbital characteristics, its nature, and its relationship to Sirius A, with accuracy that didn't exist in Western astronomy until the 20th century, when telescopes revealed what the Dogon had apparently known for millennia. Their oral traditions preserved this knowledge across generations with remarkable fidelity. The information doesn't change significantly across retellings. The details remain constant. They don't describe the characteristics of other stars, only Sirius B specifically. This isn't vague myth or poetic metaphor that could apply to multiple interpretations. It's specific astronomical knowledge about a specific invisible celestial object. The conventional explanations strain under this evidence. Perhaps some scholars suggest the Dogon observed Sirius B and we've misunderstood the visibility limitations. Perhaps they guessed correctly and maintained the guess across centuries. Perhaps they received this knowledge from another source. Each explanation becomes increasingly difficult to defend. In Peru, pre-Incan structures align to Venus's celestial movements with precision that requires regular astronomical observation across centuries. The alignments are so specific that they could only result from systematic tracking of Venus through its 8-year cycle. Creating and maintaining these alignments required knowledge, infrastructure, and commitment spanning generations. Someone had to teach the next generation how to observe Venus, how to predict its movements, how to maintain alignment markers. This is knowledge systems, not isolated achievement. These examples share a common thread. ancient peoples possessed astronomical knowledge that exceeds what we'd expect from the tools available to them. The precision of their observations, the specificity of their knowledge, the consistency of their records suggests something more sophisticated than casual sky watching. Whether this reflects sophisticated observation techniques we've lost, or contact with advanced observers, or independent discovery of astronomical principles, remains unclear. But the evidence clearly shows that ancient peoples knew more about the heavens than conventional archaeology has acknowledged. What this reveals is significant. If ancient civilizations could track celestial movements with this precision, if they could maintain astronomical knowledge across generations with this fidelity, what other sophisticated knowledge systems did they possess? If they could develop technologies for astronomical observation, might they have also developed technologies for construction, for measurement, for engineering? The astronomical knowledge becomes evidence not just of itself, but of broader ancient capability we've underestimated. Water is simple. We use it daily without thinking of it as anything remarkable. But water is also a medium through which sophisticated engineering can operate. Ancient peoples understood this. We find evidence throughout history of water-based engineering of surprising sophistication. But what we see is only the surface of what likely existed. The Egyptians developed nilometers structures designed to measure water levels. These structures aren't crude. They incorporate precision measurement and sophisticated understanding of water behavior. The measurements needed to be accurate because Egyptian civilization depended on predicting Nile flooding. Get the prediction wrong, and crops fail. Thousands starve. This created powerful incentive for precision in water measurement. The nilometers demonstrate that incentive produced results. In Cambodia, the Angkor system supported a civilization exceeding 1 million people through water management architecture of stunning sophistication. Canals, reservoirs, and distribution systems provided reliable water during both dry and wet seasons. The engineering required understanding water pressure, flow rates, and gravitational mechanics. The systems had to operate reliably year after year. This required knowledge, planning, and capability that exceeds what we often attribute to ancient peoples. Roman aqueducts are famous for their sophistication. They transported water across vast distances using gravity and pressure. The engineers who designed them understood principles of hydraulics we associate with modern science. They applied these principles in complex systems that functioned for centuries. Yet we rarely consider what else these people might have accomplished if water-based engineering was part of their sophistication. But here's where the evidence becomes truly intriguing. Ancient texts, often dismissed as mythology or poetic flourish, repeatedly reference water in construction contexts. Egyptian papyri contain references to water used in ways that don't fit purely practical purposes. Some researchers have theorized that water was central to moving massive stones. Hydraulic pressure applied precisely could position enormous weights with controlled force. If applied correctly, water could accomplish what muscle and simple tools apparently couldn't. This hypothesis remains largely untested by mainstream archaeology. The focus has remained on quarrying tools and transportation methods. Water-based technologies have received minimal investigation. Yet, if ancient peoples possessed sophisticated understanding of hydraulics and applied it to construction, the evidence might look exactly like what we see. Minimal tool marks, missing debris fields, precision that exceeds muscle capability. The water systems themselves might have been dismantled, leaving little trace. The knowledge might have been lost when civilizations transitioned, and knowledge transfer broke. This isn't speculative fantasy. It's a coherent hypothesis that explains available evidence. The absence of research into this avenue isn't because the hypothesis is inherently implausible. It's because the institutional framework hasn't prioritized investigating it. Archaeology focuses on visible material culture. Water-based systems leave less permanent trace than stone monuments or metal artifacts. Experimental investigation into water-based construction methods would be expensive and require interdisciplinary collaboration. The institutional incentives point toward maintaining conventional frameworks rather than investigating alternatives. Yet, consider what we'd expect if sophisticated water-based engineering existed in ancient times. We'd expect evidence of sophisticated hydraulic understanding in other contexts, ancient texts referencing water in construction, precise positioning of massive stones we can't explain through conventional means, minimal debris fields despite massive construction, and limited tool marks. We observe all of these. This convergence of evidence suggests we should investigate seriously whether water technology played a role in ancient engineering. The implications extend beyond construction. If ancient peoples possessed sophisticated water technology, applied it systematically to solve problems, maintained that knowledge across generations, what does this tell us about their broader technological sophistication? It suggests knowledge systems more integrated, more systematic, more sophisticated than conventional narratives acknowledge. Water becomes not just a tool for irrigation or engineering, but a window into understanding ancient capability more broadly. Every technological civilization must solve a fundamental problem: how to preserve knowledge and transmit it across generations. Without solving this problem, knowledge dies with the individuals who hold it. Civilizations collapse not just from external threats, but from the loss of the knowledge that held them together. How ancient peoples solved this problem reveals much about their sophistication. Modern culture uses writing and printing and digital storage. These systems have advantages, but also vulnerabilities. Books burn. Servers crash. Languages become dead. Digital systems become obsolete. Digital files require specific technology to access. A hard drive filled with crucial knowledge becomes useless without the proper device to read it. Ancient peoples faced analogous challenges with different technologies. Some cultures prioritized oral transmission. Knowledge was memorized, organized systematically, transmitted to the next generation through trained memory techniques. This approach worked remarkably well in cultures that developed it seriously. Certain monastic traditions maintained complex theological and philosophical knowledge through oral transmission for centuries. The techniques involved weren't magical, they were systematic. Knowledge was organized into structures, encoded in stories and narratives, attached to physical locations, reinforced through repetition and testing. When maintained rigorously, oral transmission preserves knowledge accurately across generations. Other cultures encoded knowledge into architectural form. Egyptian temples encode astronomical data in their dimensions and alignments. Mayan structures incorporate mathematical relationships. Hindu temples embed sacred knowledge in architectural proportions. These structures are permanent. They cannot be lost to fire or decay like written documents. They require no language to interpret. A person could measure a temple's proportions and extract the encoded information even if the language was dead and the writing system forgotten. Geometric information proved particularly powerful. Geometry is universal. It doesn't depend on language or cultural context. A geometric relationship true in Egypt is equally true in Peru. The proportions of a perfect square are identical whether encoded in stone or papyrus. If sophisticated knowledge was encoded geometrically, it could persist across cultures and centuries, maintained in physical form long after the civilization that created it had faded to legend. Yet what's most significant is what we don't see. Mainstream archaeology rarely finds extensive documentation of sophisticated technological knowledge. Construction records are sparse. Technical manuals are absent. Detailed instructions for building monuments don't exist in surviving texts. This absence could mean knowledge was never recorded in written form, or it could mean something more intriguing. The most sophisticated knowledge was deliberately kept restricted. Sacred knowledge, in many ancient traditions, was restricted to initiates. Not for arbitrary reasons, but because specific knowledge granted power. A civilization that maintained technological monopolies, knowledge possessed by an elite and carefully guarded, could maintain political control through that knowledge monopoly. If only the priesthood understood how to build monuments, how to predict celestial events, how to manage water systems, they maintained power. Sharing such knowledge threatened their position, so it remained restricted. This framework recontextualizes the mystery. We don't find evidence of sophisticated technology because such knowledge was deliberately obscured, not through conspiracy but through deliberate restriction within knowledge hierarchies that protected power structures. The information remained encoded in restricted texts, maintained in restricted communities, transmitted to carefully selected successors. The monuments remained as evidence of capability, but the knowledge to replicate them remained protected. This explains why we find capability without knowledge, sophistication without documentation, achievement without instruction. Mythology occupies an uncomfortable space in modern thinking. We treat it as primitive fiction, stories ancient peoples told to explain natural phenomena because they lacked scientific knowledge. This framework is partially valid. Myths do explain natural phenomena, but it dismisses an alternative possibility that's worth considering. What if myths sometimes preserved technical knowledge? Ancient peoples faced the problem of preservation. How do you keep important information intact across generations? Written documents are vulnerable. They burn, decay, get lost. But stories are robust. Stories get retold, remembered, embedded in culture. The narrative structure makes information memorable. A person remembers a story more easily than a list of facts. If you need to preserve crucial information reliably, embedding it in narrative is an effective strategy. The Mesopotamian flood myth isn't just a religious story. It contains specific measurements, specific construction details, specific references to materials and methods. If you read it not as metaphor but as technical description, it describes building a large vessel, waterproofing it, loading it with provisions. The details are oddly specific for pure mythology. A story explaining a cosmic deluge doesn't need those specifics, but a story preserving instructions for constructing a seaworthy vessel would include them. Hindu texts describe technical processes that parallel known metallurgical procedures. The Rig Veda references specific steps in metalworking, specific temperatures implied through metaphor, specific material combinations. Read these texts as purely religious, and their poetic descriptions of cosmic forces. Read them as technical manual encoded in narrative, and their instructions for advanced metallurgical processes. Both interpretations are possible, but the technical interpretation explains why the texts include specific details irrelevant to religious meaning. Egyptian mythology is saturated with measurement, alignment, and precision. The myths aren't just entertainment or spiritual instruction. They're pedagogical tools encoding technical knowledge. The relationships between deities can be understood as representing relationships between geometric principles. The journeys and transformations described in myths parallel construction processes. The numbers embedded in mythological narratives often match precisely the numbers used in temple construction. The reason myths would encode technical knowledge is clear. Sacred knowledge remains protected and unchanging. Religious texts receive meticulous preservation. They're copied carefully, maintained rigorously, transmitted with fidelity. If you encode technical knowledge in religious narrative, it receives this protection. The narrative becomes sacred, worthy of preservation, passed to successors through religious training. The technical knowledge hides in plain sight, protected by its sacred context. This wasn't necessarily deliberate deception. More likely, it was sophisticated information management. Restricted knowledge was conveyed through multiple channels. For those initiated into the knowledge system, the technical meaning was apparent. For others, the narrative remained spiritual or entertaining. This tiered system protected knowledge monopolies while maintaining it across generations. The evidence this was happening appears in how myths are actually structured. They're too specific in technical details, too precise in measurements, too consistent across cultures in certain elements to be purely invented fiction. When unrelated cultures preserve similar mythological details, similar construction narratives, similar cosmic events, similar mathematical relationships, it suggests the myths are preserving something real. Not literal events necessarily, but real technical knowledge embedded in narrative form. Consider that mythology predates writing in most cultures. Yet certain myths show remarkable consistency when written down generations or centuries later. This consistency suggests the information was maintained orally with precision. What information would warrant such careful preservation? Practical knowledge, technical knowledge, knowledge that mattered for survival or power. Spiritual narratives matter, but practical knowledge matters more when civilizations depend on it. The possibility isn't that all mythology is technical instruction. Most myths serve religious and cultural functions. But woven through certain myths are specific technical details that don't fit the religious narrative perfectly, that seem oddly precise, that appear consistently across unrelated cultures. These details might be remnants of knowledge preservation systems we've dismissed as purely spiritual. Decoding them requires reading myths with fresh questions. Not asking what cosmic truth does this represent, but asking what practical knowledge might be encoded here. This approach might reveal that ancient peoples were more systematic about preserving crucial knowledge than we've recognized, and that some of what we treat as fantasy might contain preserved technical information. We classify ancient structures into categories, and these categories shape how we interpret them. A structure is a temple, a tomb, a fortification, or a water management system. These labels feel neutral and objective, but they're actually interpretive choices that guide subsequent investigation. If you decide something is a tomb, you investigate it looking for burial chambers and grave goods. If you consider it might serve multiple purposes, you notice features that don't fit neatly into single-function interpretation. The pyramid is classified as a tomb. This classification shapes everything we look for and everything we overlook. Pyramids contain chambers. Chambers are where bodies would be placed. This interpretation seems logical, but consider what would happen if pyramids served purposes beyond burial. What if they functioned as sophisticated machines? This sounds impossible until you examine the evidence more carefully. Pyramid geometry has acoustic properties. The angles and proportions create specific resonance effects. Certain frequencies interact with the structure in particular ways. The internal passages create specific acoustic environments. These properties exist whether we interpret them as intentional or accidental. But the consistency of these acoustic properties across different pyramids suggests intention rather than accident. If pyramid builders understood acoustics and deliberately created structures with specific acoustic properties, the pyramids become machines for manipulating sound. What would be the purpose of such machines? Consider that certain frequencies affect physical material behavior. Recent research has demonstrated that ultrasonic vibrations can reduce friction between surfaces dramatically. If ancient engineers understood this principle and applied it, sound technology could facilitate moving massive stones. The pyramids might have functioned as resonance chambers, generating specific frequencies that served a purpose during construction or maintenance. The chambers inside might have been functional elements, not burial spaces. Stonehenge presents a similar puzzle. Its configuration creates specific acoustic and astronomical alignments. It's classified as a temple, but consider it might have been a functional device whose operation we haven't understood. The stone arrangement creates lines of sight to specific celestial events. It also creates acoustic patterns when sounds occur within the structure. What if it served as an astronomical observation instrument combined with an acoustic device? The massive effort required to transport stones from miles away, the precise alignment, the specific geometric arrangement, all could reflect a functional purpose we've misidentified. The Great Sphinx sits at the apex of sophisticated geomantic markers spanning the plateau. Its construction is extraordinary. Its positioning is mathematically significant. Its astronomical alignments align with specific celestial events. What if the Sphinx served as a focal point or marker for a larger system? What if it functioned as part of coordinated technology spanning the entire plateau, with different structures serving different functions but operating as an integrated system? This interpretation requires setting aside our categorical assumptions. It asks, what if we're wrong about what these structures were for? Not based on evidence proving they were machines, but based on evidence that contradicts simple functional categorization. If pyramids have sophisticated acoustic properties, shouldn't we investigate whether these were intentional? If Stonehenge creates specific astronomical and acoustic conditions, shouldn't we examine whether these served a purpose? If Sphinx positioning encodes mathematical relationships, shouldn't we ask why? The evidence doesn't prove monuments were machines, but it does show that classifications we've taken for granted might be incomplete. Tombs can also be acoustic resonators. Temples can also be astronomical instruments. Structures can serve multiple functions. Recognizing this opens interpretive possibilities we've closed off through categorical assumptions. It invites investigation rather than confident assertion that we know what these monuments were built to do. Sophisticated technologies vanish from history. This isn't speculation. This is documented fact. When civilizations transition, when knowledge transfer breaks, when institutional continuity fractures, capabilities can disappear entirely. Understanding how this happens illuminates how ancient knowledge might have been lost. The knowledge that built Roman aqueducts was lost after Rome's fall, Medieval Europeans couldn't replicate Roman concrete. They tried. Their structures were inferior. The knowledge of specific material ratios, curing techniques, and application methods had been lost. It took centuries to rediscover what Romans had known. The technology existed. The monuments remained. But the knowledge to replicate it was gone. Damascus steel represents another example. Medieval smiths created steel with properties modern metallurgists couldn't match until recently. The knowledge of how to create it was lost. The steel remained in surviving weapons, fascinating and mysterious. The technique was eventually partially rediscovered through reverse engineering and experimentation, but not before centuries passed when the capability had completely vanished from human memory. These examples teach us something crucial. Knowledge loss occurs through systematic causes. When master craftspeople die without teaching successors, knowledge dies with them. Wars that kill both experienced practitioners and apprentices break transmission chains. When civilizations fragment, the institutional structures supporting knowledge transfer collapse. When economic systems change, craftspeople switch to different trades. When political systems shift, knowledge monopolies lose value and protection. Knowledge isn't invulnerable, it's fragile. It requires active transmission, institutional support, economic incentive, and cultural value to persist. The Bronze Age collapse saw sophisticated civilizations crumble simultaneously across the Mediterranean. Trade networks that had existed for centuries vanished. Literacy disappeared in certain regions. Sophisticated craftsmanship declined. Fewer people could construct large vessels. Fewer people understood navigation. The capability existed briefly, then disappeared. What remained were ruins and legends of a golden age more sophisticated than what followed. During such transitions, knowledge loss occurs through multiple mechanisms. Deliberately in some cases. When new religious frameworks rise, they sometimes delegitimize older knowledge systems. The Abrahamic faiths, as they expanded, sometimes suppressed prior knowledge traditions. This wasn't universal. Many texts were preserved through religious institutions. But some knowledge systems, particularly those tied to competing religious structures, were disrupted or lost. The Apollo temples that contained astronomical knowledge were replaced by Christian churches. The knowledge wasn't necessarily destroyed, but institutional support for transmitting it was. Knowledge loss also occurs accidentally through disruption of ordinary transmission. When schools close, students don't learn. When apprenticeship systems break, skills aren't passed down. When libraries burn, written knowledge vanishes. These disruptions seem obvious in retrospect, but they're devastating in the moment. A single generation where knowledge isn't transmitted successfully and the knowledge is lost. The next generation inherits fragments and legends, but not working understanding. Technological obsolescence contributes as well. When a civilization develops new methods that supersede old ones, the old knowledge seems less valuable. Why maintain knowledge of ancient techniques when newer methods work better? But if something happens to the newer methods, loss of required materials, loss of economic support, loss of institutional structures, the old knowledge isn't available. It's been abandoned and lost. Some knowledge loss occurs through deliberate suppression and restriction. Sacred knowledge maintained by priesthoods might be deliberately obscured, encoded, restricted. If the priesthood is disrupted by conquest, by religious transformation, by institutional collapse, the knowledge might be lost forever. The restricted status that protected it also makes it fragile. If the restricted community is destroyed, the knowledge dies with it. What emerges from examining these historical examples is a pattern. Knowledge loss is comprehensible. It occurs through understood mechanisms. Civilizations transition. Knowledge transfer breaks. Capabilities vanish. This pattern provides a framework for understanding how even sophisticated ancient knowledge could be lost. We don't need to invoke mystery or magic. History proves that knowledge loss happens regularly. The question isn't whether ancient knowledge could be lost. The question is what was lost, and whether traces remain that we might decipher. When you examine ancient civilizations individually, each is remarkable. Egyptian engineering stands alone. Mayan mathematics seems exceptional on its own. Indian architectural sophistication appears unique. Pre-Incan construction demonstrates incredible capability. But when you step back and look at all of them together, something shifts. Patterns become visible that individual sites don't reveal. Across completely isolated civilizations, we find similar approaches to fundamental challenges. The precision required in Egyptian temples appears again in pre-Incan construction on the other side of the world. The astronomical knowledge demonstrated at Nabta Playa appears in Mayan codices, separated by centuries and continents. The mathematical relationships embedded in architectural proportions show up consistently across cultures. These similarities could result from coincidence, but the convergence suggests something more systematic. Consider the pyramid form itself. Egypt built pyramids, but so did other civilizations. Pre-Columbian Mesoamericans built pyramid structures. The similarities aren't just architectural form, but engineering approach. The precision, the astronomical alignments, the mathematical relationships, these recur across cultures that had no documented contact. Multiple explanations are possible. Humans, when reaching certain technological levels, might independently discover similar solutions to similar problems. This is convergent evolution in technology. Or knowledge was transmitted across cultures in ways our historical narratives don't capture. Trade networks might have transmitted principles even if direct contact was limited. The geometric principles appear universally. Certain angles, certain proportions, certain relationships between structures recur. The golden ratio, pi, mathematical constants, appear encoded in structures across cultures. These mathematical relationships couldn't be discovered through accident. They result from deliberate investigation and application. When the same mathematical principles appear across unrelated cultures, it suggests either independent discovery of universal mathematical truth or knowledge transmission between cultures. Water management offers another pattern. Multiple civilizations developed sophisticated irrigation systems, canal networks, and water distribution methods. The engineering challenges are similar across geographic regions. Arid civilizations need similar solutions. They independently developed similar approaches. But some civilizations went further, creating water management systems of surprising sophistication that exceed what their geographic situation strictly required. Why would a civilization invest effort in more sophisticated water management than necessary? Perhaps because the systems served additional purposes. Perhaps the knowledge extended to applications beyond simple irrigation. The pattern that emerges when looking across civilizations is one of sophistication, not isolated achievements, but consistent capability. Multiple domains of knowledge: astronomy, mathematics, geometry, engineering, water management. These knowledge domains weren't independent. They integrated. A civilization possessing sophisticated astronomical knowledge likely also had sophisticated measurement capability. Measurement capability enabled both construction precision and water management. Water management related to astronomical observation for agricultural planning. The knowledge domains connected into integrated systems. This systemic integration suggests something important. We're not looking at scattered achievements by lucky or particularly brilliant individuals. We're looking at knowledge systems that were learned, taught, maintained, and applied systematically. The consistency of these systems across cultures suggests they weren't invented fresh by each civilization, but rather represent approaches discovered and refined through cultural transmission. What this means for understanding ancient capability is significant. These weren't anomalies or miraculous achievements. They were expected outputs of knowledge systems that worked effectively. If a civilization possessed such integrated knowledge, astronomy, mathematics, engineering, water management, material science, the monuments and achievements we observe become unsurprising. They're the natural results of sophisticated people applying sophisticated knowledge. The question this raises is about knowledge scope. If these domains were understood and integrated, what other knowledge domains might have been equally sophisticated? Medicine, metallurgy, chemistry, psychology? We have limited evidence from surviving texts and artifacts, but the pattern suggests that sophisticated knowledge likely extended across multiple domains. A culture with integrated geometric, mathematical, and engineering knowledge probably also possessed sophisticated material science to know which stones could be cut effectively, which tools would work best, which materials would endure. Understanding ancient sophistication through this lens of pattern and integration changes the interpretation of individual mysteries. The precision at Giza isn't a lucky accident, but an expected result of integrated knowledge. The astronomical alignments at various sites reflect systematic application of astronomy across cultures. The structures aren't mysterious exceptions to primitive history. They're expressions of sophisticated knowledge systems that were working effectively. The real mystery becomes not how they achieved what they did, but why we've dismissed their capability for so long, and what knowledge systems might have enabled their achievements. Beyond monuments and astronomical alignments, archaeology has recovered artifacts that demonstrate technical knowledge exceeding conventional assumptions about ancient capability. These artifacts exist. They're in museums. They've been examined by experts. Yet their implications often remain understated in mainstream narratives. The Baghdad battery consists of a clay jar containing copper and iron electrodes and acidic material. Whether it functioned as an electrical power source is debated among researchers. But the design itself demonstrates electrochemical knowledge. Someone understood that copper and iron in an acidic solution would create an electrochemical reaction. This is sophisticated knowledge. It's knowledge that serves no obvious practical purpose if not applied to generate electrical current. Why would someone design this setup unless they understood what it would do? The Antikythera mechanism represents even more striking evidence. This device, discovered in a Greek shipwreck, consists of gears and mechanical sophistication rivaling 18th century precision instruments. It calculated astronomical positions. It's an analog computer. Its existence proves that ancient Greeks possessed mechanical sophistication we didn't expect. The knowledge required to design and build this mechanism is genuine expertise. For decades after discovery, scholars couldn't fully understand the mechanism. It took modern analysis to decode how it worked. This is humbling. An ancient device, so sophisticated that modern experts struggled to understand it. Indian iron pillars demonstrate metallurgical sophistication. The iron is rust-resistant to a degree that modern metallurgists still can't fully replicate. The process that created this steel is lost. The pillars remain as evidence of capability that vanished. Modern researchers have attempted to reverse engineer the process, with limited success. The metallurgical knowledge that created these pillars clearly exceeded what we'd expect from ancient technology. These aren't isolated curiosities. They're evidence of technical domains where ancients achieved mastery. The Baghdad battery tells us about electrochemistry. The Antikythera mechanism tells us about mechanical engineering and astronomy. The Indian pillars tell us about metallurgy. Each artifact reveals a knowledge domain where ancients were working at sophisticated levels. What makes these artifacts particularly significant is how they've been treated in mainstream discourse. They're known, they're studied, but their implications aren't integrated into broader understanding of ancient capability. Instead, they're treated as exceptional anomalies rather than evidence of systematic technical sophistication. The Baghdad battery is presented as they had some electrochemical knowledge, but probably didn't use it for electricity. The Antikythera mechanism becomes a remarkable device, but probably isolated. The Indian pillars become remarkable metallurgy, but we don't know why. This pattern of minimizing implications is itself revealing. When evidence confirms mainstream narratives, it's promoted and emphasized. When evidence challenges narratives, it's acknowledged, but its implications are downplayed. This bias operates mostly unconsciously within academic discourse, but it shapes which evidence becomes culturally significant and which remains marginalized. Consider what these artifacts tell us collectively. Electrochemistry, mechanical engineering, sophisticated metallurgy, and the other domains represented by these artifacts aren't independent. They require mathematical knowledge, geometric understanding, material science, and problem-solving approach. An ancient culture, capable of all these things, simultaneously possessed integrated technical knowledge of considerable sophistication. If we trust the artifacts and their physical evidence, we can examine directly. We must conclude that ancient peoples achieved technical mastery in multiple domains. The mysteries surrounding how they accomplished their monuments become less about whether they could accomplish such things, and more about which specific methods and knowledge systems enabled the achievements. The artifact evidence doesn't answer that question definitively, but it strongly supports the conclusion that ancient peoples possessed the technical sophistication to accomplish remarkable things. Beyond monuments and astronomical alignments, archaeology has recovered artifacts that demonstrate technical knowledge exceeding conventional assumptions about ancient capability. These artifacts exist. They're in museums. They've been examined by experts. Yet their implications often remain understated in mainstream narratives. The Baghdad battery consists of a clay jar containing copper and iron electrodes and acidic material. Whether it functioned as an electrical power source is debated among researchers, but the design itself demonstrates electrochemical knowledge. Someone understood that copper and iron in an acidic solution would create an electrochemical reaction. This is sophisticated knowledge. It's knowledge that serves no obvious practical purpose if not applied to generate electrical current. Why would someone design this setup unless they understood what it would do? The Antikythera mechanism represents even more striking evidence. This device, discovered in a Greek shipwreck, consists of gears and mechanical sophistication rivaling 18th century precision instruments. It calculated astronomical positions. It's an analog computer. Its existence proves that ancient Greeks possessed mechanical sophistication we didn't expect. The knowledge required to design and build this mechanism is genuine expertise. For decades after discovery, scholars couldn't fully understand the mechanism. It took modern analysis to decode how it worked. This is humbling. An ancient device, so sophisticated that modern experts struggle to understand it. Indian iron pillars demonstrate metallurgical sophistication. The iron is rust-resistant to a degree that modern metallurgists still can't fully replicate. The process that created this steel is lost. The pillars remain as evidence of capability that vanished. Modern researchers have attempted to reverse engineer the process, with limited success. The metallurgical knowledge that created these pillars clearly exceeded what we'd expect from ancient technology. These aren't isolated curiosities. They're evidence of technical domains where ancients achieved mastery. The Baghdad battery tells us about electrochemistry. The Antikythera mechanism tells us about mechanical engineering and astronomy. The Indian pillars tell us about metallurgy. Each artifact reveals a knowledge domain where ancients were working at sophisticated levels. What makes these artifacts particularly significant is how they've been treated in mainstream discourse. They're known. They're studied. But their implications aren't integrated into broader understanding of ancient capability. Instead, they're treated as exceptional anomalies rather than evidence of systematic technical sophistication. The Baghdad battery is presented as they had some electrochemical knowledge, but probably didn't use it for electricity. The Antikythera mechanism becomes a remarkable device, but probably isolated. The Indian pillars become remarkable metallurgy, but we don't know why. This pattern of minimizing implications is itself revealing. When evidence confirms mainstream narratives, it's promoted and emphasized. When evidence challenges narratives, it's acknowledged, but its implications are downplayed. This bias operates mostly unconsciously within academic discourse, but it shapes which evidence becomes culturally significant and which remains marginalized. Consider what these artifacts tell us collectively. Electrochemistry, mechanical engineering, sophisticated metallurgy, and the other domains represented by these artifacts aren't independent. They require mathematical knowledge, geometric understanding, material science, and problem-solving approach. An ancient culture capable of all these things simultaneously possessed integrated technical knowledge of considerable sophistication. If we trust the artifacts and their physical evidence, we can examine directly. We must conclude that ancient peoples achieved technical mastery in multiple domains. The mysteries surrounding how they accomplished their monuments become less about whether they could accomplish such things, and more about which specific methods and knowledge systems enabled the achievements. The artifact evidence doesn't answer that question definitively, but it strongly supports the conclusion that ancient peoples possessed the technical sophistication to accomplish remarkable things. Before proceeding further into speculation, we must establish clearly what we actually know with confidence. Distinguishing demonstrated facts from interpretation requires discipline. It means acknowledging what evidence supports and what it doesn't. Ancient peoples demonstrably achieved precision in stone construction. We can measure this. The blocks at Giza fit with extraordinary tightness. The angles at Pumapunku are exact. These aren't interpretations. They're physical facts we can verify by direct examination. Ancient peoples clearly possessed the capability to cut and position stones with high precision. How they achieved this precision remains partially mysterious, but the precision itself is undeniable. Ancient peoples demonstrably possessed sophisticated astronomical knowledge. The alignments at various sites correlate with astronomical events too precisely to be accidental. The Dogon knowledge of Sirius B is documented. The Mayan astronomical calculations are recorded. This knowledge existed. Whether they possessed telescopes or other observation technology beyond naked eye observation remains uncertain, but that they possessed genuine astronomical knowledge is established. Ancient peoples demonstrably understood and applied mathematical principles. The golden ratio appears in proportions of structures across cultures. Pi is embedded in pyramid geometry. Mathematical relationships in Mayan architecture are verifiable. They possessed working mathematics, whether or not they possessed formal mathematical notation, as moderns understand it. Ancient peoples demonstrably built sophisticated water management systems that functioned effectively for extended periods. The Egyptian nilometers worked. The Angkor system supported massive population. Roman aqueducts transported water across great distances. This expertise is demonstrated through surviving systems. These demonstrable facts establish that ancient peoples possessed genuine technical sophistication. This itself contradicts narratives that present them as primitive or limited in capability. Sophistication in multiple domains, astronomy, geometry, mathematics, engineering, indicates that capacity for complex thought and systematic knowledge application. Now, what doesn't the evidence demonstrate? The evidence doesn't show how specific construction methods operated in detail. We have theories, but limited direct evidence of methods. The evidence doesn't prove sophisticated technologies beyond what visible artifacts suggest. We might speculate about lost technologies, but we can't claim them as established fact. The evidence doesn't explain some of the mechanisms that might have enabled their achievements. We have gaps. What's crucial is holding this line clearly. Demonstrable facts on one side, speculation on the other. Some interpretations sit in between plausible given evidence but not definitively proven. This three-tier approach maintains intellectual rigor. Consider the precision paradox again, with these distinctions clear. The precision is demonstrable. It's physically measurable. The conventional explanation that copper chisels and manpower achieved this is interpretive. It's unsupported by experimental evidence. Alternative mechanisms might also explain the precision, but none have been definitively proven. So precision is fact. Methods remain uncertain. This framework prevents the documentary from becoming either mainstream dogmatism or fringe speculation. We acknowledge facts. We discuss plausible interpretations. We distinguish between what's proven and what's speculative. We maintain intellectual rigor by refusing to present certainty where uncertainty exists. What's remarkable about maintaining these distinctions is how it shifts perspective. Instead of, we know how they built the pyramids, even though the explanation is problematic, we can say, we know they built the pyramids with precision that exceeds conventional explanations. We know they possessed technical sophistication. We don't fully know the methods they employed. This is more honest and more interesting. The honest answer to many ancient mysteries is, we don't know. We have evidence they achieved remarkable things. We have incomplete understanding of how. Multiple frameworks could explain available evidence. Some frameworks are better supported than others, but none are definitive. This uncertainty isn't failure. It's accurate reflection of actual state of knowledge. Once we've established what we know, we can examine what remains plausible but unproven. This category is crucial. It contains genuine possibilities worth investigating that we can't yet claim as established. Acoustic technology for construction purposes falls into this category. We know ancient structures have acoustic properties. We know sound and vibration affect material behavior. We know ancients understood and applied acoustic principles in other contexts. Therefore, it's plausible they developed acoustic engineering for construction. But we lack direct evidence that this occurred. It's plausible, not proven. Water-based construction methods similarly fall here. We know ancients understood hydraulics. We know they applied hydraulic engineering successfully in other domains. We know water could theoretically accomplish tasks muscle alone couldn't. So it's plausible they developed sophisticated water engineering for construction. But we lack definitive evidence. The theory explains gaps in conventional methodology, but plausibility isn't proof. Sophisticated measurement and geometric systems based on principles ancients clearly possessed fit this category. We know they measured with precision. We know they understood geometric relationships. Systems using these known principles to achieve even greater precision are theoretically possible. But documenting exactly what systems existed and how they functioned requires evidence we don't possess. It's plausible but unproven. Restricted knowledge systems maintained by priesthoods or specialized guilds fit here. We know such systems existed in various ancient cultures. We know restricted knowledge serves to maintain power and control. Therefore, it's plausible that the most sophisticated technical knowledge was restricted and carefully guarded. But proving this for ancient Egypt or other civilizations requires evidence of restriction that we largely lack. Plausible, but uncertain. What separates plausible from speculative? Plausible explanations use principles ancients demonstrably possessed. Plausible explanations fit available evidence without massive contradiction. Plausible explanations are internally coherent. Speculative explanations require unknown principles, often contradict available evidence, or require multiple unlikely coincidences. So technological systems using water, sound, or geometric principles fall into plausible. Technologies requiring unknown physics, or requiring massive conspiracies to hide evidence, or requiring belief in lost superscience fall into speculative. The value of maintaining this distinction is that plausible unknowns become legitimate research areas. If acoustic engineering for construction is plausible, experimental investigation becomes appropriate. Testing could confirm or refute the hypothesis. If water-based systems are plausible, experimental recreation and analysis could clarify whether such systems would actually work at required scales. The plausible unknowns become testable hypotheses rather than settled facts or dismissed impossibilities. Currently, mainstream archaeology doesn't systematically investigate plausible unknowns in these categories. The methodological bias toward conventional explanations means alternative plausible frameworks don't receive serious investigation. Yet science typically progresses by investigating what's plausible and determining through experimentation and evidence analysis whether possibilities are actual. Ancient mysteries present excellent opportunities for this investigation. Consider what would happen if we took plausible unknowns seriously. We'd establish research programs investigating specific hypotheses. We'd conduct experiments testing whether plausible methods could achieve observable results. We'd examine sites with questions derived from plausible frameworks rather than only from conventional approaches. We'd potentially discover that some mysteries resolve through investigation, while others remain genuinely uncertain. The implications would be significant. If investigation revealed that sophisticated methods we hadn't considered were actually employed, our understanding of ancient capability would deepen. If investigation revealed that conventional explanations, when properly tested, actually work better than alternatives suggest, we'd have more solid ground for confidence in standard narratives. Either way, investigation advances understanding. Dismissing plausible unknowns without investigation simply protects current paradigms from challenge. Archaeological methodology has inherent blind spots. Understanding these limitations helps explain why certain evidence might be invisible to conventional investigation. Archaeology searches for material culture, pottery, tools, structures, written records. These survive in the archaeological record. But technologies that leave minimal physical trace remain archaeologically invisible. If construction relied on systems now completely dismantled and reused, what evidence would remain? Minimal. Channels that could be misidentified as decoration or drainage, holes that seem accidental rather than structural, geometric relationships in standing monuments that could represent accident rather than intention. Wooden structures decompose. If crucial construction systems used wooden frameworks, ramps, or temporary apparatus, and if these were carefully dismantled and reused, almost no trace would remain after millennia. Wooden post holes decay. The patterns become invisible. A construction method dependent on sophisticated wooden systems could leave almost no archaeological signature, despite being tremendously important during the actual construction period. Knowledge systems themselves leave limited material trace. If technical expertise was maintained through oral transmission and practical training rather than written texts, what physical evidence would remain? Monuments built by that knowledge, but not the knowledge itself. The methodology itself might be archaeologically invisible, even as its results are physically obvious. Precision measurement systems leave ambiguous traces. If ancients created measurement tools, sophisticated instruments for precision and alignment, these could appear as ordinary objects to archaeologists unfamiliar with their function. A measuring device might look like a tool for something else. Without context, without understanding the actual purpose, the artifact could be misclassified or minimized as unimportant. Water-based systems present particular challenges. Water leaves minimal permanent trace. If construction relied on temporary water channels, pressure systems, or hydraulic apparatus, and if these left no permanent structures, archaeology might miss them entirely. We'd see results of their work, precisely positioned stones, but not understand the methods, because the apparatus itself left no archaeological signature. Sound and vibration systems similarly leave ambiguous traces. The effects might be visible precisely shaped and positioned stones, but the methods might be archaeologically invisible. If construction employed sound frequencies in ways we don't yet understand, the evidence would be the monuments, not the mechanisms that created them. The mechanisms themselves might have been simple apparatus that left no permanent trace. This pattern is important. The more sophisticated and effective a technology, the less waste and debris it might generate. Efficient methods leave minimal trace. Inefficient methods leave obvious evidence of mistakes, failed attempts, and abandoned approaches. If ancient peoples developed sophisticated technologies, these might leave less archaeological signature than less effective methods would. Conventional archaeology, not recognizing these invisible technologies, attributes monuments to less sophisticated methods. The evidence for those methods is thin, hence the gaps and contradictions we observe. But the alternatives, if they left minimal trace, would be equally archaeologically invisible. This creates asymmetry. Conventional explanations appear inadequate, but alternatives remain invisible to archaeological methodology. Understanding this limitation invites different approaches. Rather than only searching for physical evidence of methods, we might analyze monuments to reverse engineer what methods they required. Rather than assuming conventional tools, we might test what methods would actually produce observed results. Rather than dismissing plausible technologies as speculative, we might investigate whether evidence of them could survive archaeologically. These approaches wouldn't replace traditional archaeology. They'd complement it, broadening investigation toward possibilities conventional methodology might miss. Mainstream archaeology presents ancient civilizations as isolated until surprisingly recent contact. The narrative runs. For most of human history, civilizations developed separately, cut off from one another. Then, gradually, contact increased. Trade networks emerged. Knowledge flowed between cultures. Finally, in recent centuries, globalization connected everything. This narrative is increasingly difficult to defend given accumulating evidence. Isolation was far less complete than standard models suggest. Contact was more extensive, more frequent, and more ancient than we've acknowledged. Knowledge networks spanned greater distances than we typically recognize. The timeline of connection reaches much further backward than conventional frameworks allow. The evidence is substantial. Pre-Columbian American civilizations possessed knowledge of Asian crops. How would crops native to Asia appear in the Americas before Columbus, if no contact occurred? The most straightforward explanation: boats crossed the Pacific. We find evidence of Polynesian settlements reaching far into the Pacific. Asian vessels were capable of ocean voyaging. It's entirely plausible that some reached American shores centuries before documented European contact. Phoenician explorers reached beyond the Mediterranean. Historical records suggest they explored the Atlantic coast of Africa, and possibly beyond. If their reach extended to Atlantic islands, further voyages to the Americas aren't impossible. Navigation skills necessary for such voyages are within capability that ancient peoples demonstrably possessed. Indian traders established extensive networks spanning thousands of miles. trade routes connected India with Southeast Asia, China, and beyond. These networks existed for centuries, moving goods and ideas across vast distances. If trade reached so far, knowledge traveled with merchants. Astronomical observations, mathematical principles, engineering approaches, these would flow through trade networks. Egyptian ships conducted ocean voyages. Historical records document expeditions down the Red Sea and presumably beyond. If Egyptian maritime capability extended to sustained ocean voyaging, contact with distant civilizations becomes possible. Recent research has suggested Egyptian influence in certain ancient American structures. Whether this reflects actual Egyptian presence or misinterpretation of architectural similarities remains debated. But the debate reflects recognition that contact possibilities exist. What emerges from examining this evidence is a picture of ancient world significantly more connected than isolation models suggest. Contact was probably rare and limited compared to modern globalization, but it wasn't non-existent. Knowledge networks operated across surprising distances. Information flowed, though probably slowly and selectively. Trade routes connected distant regions. The possibility of knowledge transmission through these networks is real. This doesn't necessarily explain similar technologies appearing across civilizations. Diffusion of specific knowledge would be slow, selective, probably filtering through multiple intermediaries. Information would be distorted in transmission. Yet it's conceivable that fundamental principles, geometric relationships, astronomical observations, mathematical concepts, could be transmitted through trade networks. Merchants recognizing useful knowledge could carry it to new markets. Craftspeople encountering new methods could adopt and adapt them. Alternatively, the similarities between distant civilizations might reflect independent discovery rather than diffusion. Humans, when facing similar challenges with similar resources, often discover similar solutions. The pyramid form emerges logically as solution for monumental construction in specific geographic contexts. Mathematical constants like pi would be independently discovered by any culture systematizing geometry. Astronomical knowledge would accumulate independently wherever people studied the skies systematically. Either mechanism diffusion through trade networks or independent discovery would explain why isolated civilizations developed similar technologies. The evidence doesn't definitively distinguish between them, but recognizing both possibilities is important. It prevents assuming knowledge flowed through diffusion when independent development might better explain the evidence. It also prevents assuming complete independence when some contact and knowledge transmission might have occurred. The implication for understanding ancient mysteries is significant. If civilizations were more connected than isolation models suggest, similarities in technology and knowledge become easier to explain. If knowledge could flow through networks, discovering that Egyptian and Mayan astronomical techniques share principles becomes less surprising. If information could be exchanged through trade, finding similar mathematical applications across cultures becomes comprehensible. The mysteries don't disappear, but they shift from how did isolated civilizations independently develop identical knowledge to how extensively was knowledge shared through ancient networks. At the extreme edge of speculation lies a question so controversial that most scholars avoid it. What if historical sources and archaeological evidence don't completely account for all influences on ancient civilizations? This isn't proposing aliens or supernatural intervention. It's simply asking whether information might be missing from our historical narrative. Our historical record is incomplete. We know this with certainty. Ice ages erased evidence. Civilizations destroyed written records. Floods and earthquakes buried sites. Wars destroyed libraries. What survived is a fraction of what existed. For every city we've excavated, hundreds remain undiscovered. For every ancient text we possess, countless were lost. The historical record contains vast gaps. Archaeological evidence regularly revises our understanding of history. We discover older civilizations than expected. We find evidence of contact we didn't suspect. We encounter technologies we didn't think existed. These discoveries don't contradict previous understanding accidentally. They show that our understanding was incomplete. If the past regularly surprises us, claiming certainty about it is premature. Some researchers propose advanced Ice Age cultures predating known civilizations. Evidence of human habitation during Ice Age exists. Some anthropologists suggest sophisticated societies might have existed before the retreat of glaciers transformed geography. These civilizations might have left minimal archaeological trace or been destroyed by geological transformation. This is speculative, but not absurd. The Ice Age ended only 12,000 years ago. The margin between then and civilization emergence is narrow. Mythological references across cultures mention advanced beings teaching humanity. Different traditions describe this differently. Hindu texts reference beings of great wisdom. Mesopotamian texts describe Anunnakian watchers. Egyptian texts reference beings of great knowledge. Pre-Columbian texts describe civilizing founders. These could be metaphor for natural discovery of knowledge. Or they could preserve memory of contact with peoples more advanced technologically than surrounding populations. Consider this scenario without requiring belief in it. What if a civilization achieved significant technological sophistication, then experienced catastrophe that reduced them but didn't eliminate them entirely? Survivors might encounter other peoples, teaching them techniques and principles. This knowledge would persist in the traditions of peoples who received it, perhaps transformed through retelling into legend of advanced beings. Multiple civilizations receiving such knowledge would develop similar technologies. The source civilization might be lost to history, but their influence would appear in practices across distant cultures. This is speculation. The evidence doesn't support it, but the evidence doesn't exclude it. Our historical understanding is too incomplete to claim certainty. This distinction matters. Claiming, "We know ancients developed technologies independently," is overconfident. Saying, "Available evidence suggests they did, but we can't exclude other possibilities," is honest. What distinguishes plausible from unlikely in this speculative territory? Plausible scenarios use mechanisms and explain evidence observed. Unlikely scenarios require massive cover-ups, implausible transmission of information, or violation of known principles. A lost advanced civilization teaching nearby peoples is plausible because mechanisms exist for this, and it explains observed similarities. Alien intervention is less plausible because it requires mechanisms we have no evidence for, and raises questions about why intervention left such ambiguous traces. The intellectual honest response to vast historical gaps is humility. We don't know everything. Multiple scenarios are consistent with partial evidence. This doesn't mean all scenarios are equally likely. Some are better supported than others, but recognizing that our knowledge is incomplete and alternative frameworks remain possible is appropriate given the state of evidence. This investigation has moved from solid evidence through plausible unknowns into genuine speculation. At this juncture, acknowledging limits of historical knowledge is crucial. History isn't a solved puzzle. Despite centuries of research, major questions remain genuinely uncertain. How did pyramids get built? We don't know definitively. How extensive was ancient contact between civilizations? We don't know completely. What knowledge systems ancients possessed? We have fragments. The archaeological record remains riddled with gaps and mysteries. These gaps don't indicate research failure. They reflect fundamental limitations. We're investigating past using fragmentary evidence. Some materials survive, others don't. Some structures remain, others are destroyed. Some writing persists, much is lost. Understanding complete history using partial evidence is inherently limited. This reality permits multiple frameworks interpreting available evidence. Conventional frameworks emphasizing independent discovery and isolation explain some observations. Frameworks emphasizing contact and knowledge diffusion explain others. Frameworks proposing unknown sources or advanced predecessors explain still others. No single framework perfectly accounts for everything. This situation is intellectually frustrating. We want certainty. We want to know definitively how things happened. But the evidence doesn't permit certainty. Honest assessment requires acknowledging this. It requires resisting the temptation to claim confidence we don't possess. It requires recognizing that mystery isn't failure, but honest reflection of actual state of knowledge. What we can do is investigate systematically. We can test hypotheses. We can examine assumptions. We can gather more evidence through careful excavation and analysis. We can gradually improve understanding, even without achieving complete certainty. Science operates under conditions of incomplete knowledge all the time. Astronomy deals with objects we'll never touch. Geology reconstructs processes we can't observe. Psychology investigates consciousness we can't directly access. Science accommodates uncertainty while pursuing understanding. Ancient mysteries should receive similar approach. We can investigate seriously without claiming false certainty. We can test alternative frameworks without endorsing speculative possibilities as proven. We can acknowledge gaps while respecting the genuine evidence and sophistication we do observe. This approach maintains intellectual rigor while remaining open to genuine investigation and possible revision as evidence accumulates. Setting aside speculation and focusing purely on demonstrated evidence, ancient peoples achieved engineering feats requiring genuine sophistication, technical skill, and systematic knowledge. This isn't controversial among serious scholars, though popular understanding sometimes misses it. Consider the precision. The Great Pyramid's base deviates by mere inches across a perimeter exceeding 750 feet. Achieving this precision, without laser measurement, without digital technology, without modern instruments, is genuinely impressive. Modern construction typically tolerates larger variation. Ancient builders exceeded modern standards in some respects. This precision didn't happen by accident. It required intention, skill, and capability. The astronomical alignments at various sites are equally undeniable. Nabta Playa's alignment with Orion's belt is precise enough that it couldn't result from coincidence. Mayan astronomical predictions were accurate enough that we still reference them. Egyptian temples align to celestial events, with specificity requiring systematic observation. Achieving this astronomical knowledge required observation, calculation, and preservation of data across generations. This is genuine accomplishment. The water management systems that functioned for centuries demonstrate engineering capability. Nilometers measured water with precision necessary for civilization survival. Angkor's systems supported population exceeding 1 million for extended periods. Roman aqueducts transported water across vast distances. These systems worked. They functioned reliably. Designing and maintaining such systems requires knowledge, skill, and planning. The mathematical relationships embedded in structures worldwide reveal systematic understanding. The golden ratio appearing across cultures in architectural proportions isn't accident. Pi encoded in pyramid geometry isn't coincidence. These mathematical relationships required deliberate application. Ancients understood and applied mathematics systematically. What this demonstrates collectively is that ancient peoples were intelligent, capable, and technically sophisticated. They solved complex problems. They built lasting monuments. They accumulated and maintained knowledge across generations. They developed systematic approaches to engineering and astronomy. This is demonstrable. It requires no speculation or theory. The evidence itself proves sophistication. The implications are significant. If ancients were sophisticated enough to accomplish these things, the conventional narrative portraying them as primitive or limited becomes untenable. They weren't primitive. They were different. Their knowledge emphasized different domains than modern knowledge. Their technology focused on different challenges than ours. But they were capable of genuine sophistication. This recognition should reshape how we approach ancient mysteries. Instead of asking, how could primitive people accomplish this? We should ask, what knowledge systems enabled capable people to accomplish this? The question changes when you respect ancient capability. Instead of skeptical dismissal, you pursue genuine investigation. Instead of claiming certainty about methods we can't fully trace, you acknowledge that sophisticated knowledge likely enabled observed achievements even if specifics remain unclear. The evidence also suggests that some knowledge domains where ancients achieved sophistication, certain engineering approaches, specific astronomical observations, particular mathematical applications were subsequently lost. We have the monuments they built, but not complete understanding of how they built them. We have the astronomical observations they recorded, but not the full measurement systems they employed. We have the mathematical relationships they embedded, but not complete knowledge of how they discovered them. This partial inheritance is historically common. Civilizations rise, develop sophistication in specific domains, then decline and lose that sophisticated knowledge. The mechanisms of loss are well documented. Knowledge loss is real. Understanding this helps us avoid both extremes: the assumption that ancients were impossibly advanced, and the dismissal of them as primitively limited. They were capable people who achieved genuine sophistication in specific domains. That knowledge was partially lost through historical transition. What remains allows us to glimpse their capability while acknowledging we don't fully understand their methods. History contains clear transition points where knowledge systems shifted significantly, capabilities declined, and sophisticated understanding was partially lost. Understanding these transitions illuminates how knowledge loss happens and provides framework for comprehending what might have been lost in ancient times. The Bronze Age collapse represents one of the most significant transitions in recorded history. Around 1200 BCE, sophisticated civilizations spanning the Mediterranean Egypt, Mycenaean Greece, the Hittite Empire, and others crumbled nearly simultaneously. Trade networks that had existed for centuries vanished. Writing systems disappeared in some regions. Literacy declined. Archaeological evidence shows technological regression. Civilizations that had been building sophisticated monuments suddenly couldn't maintain previous capability. What caused this collapse remains debated. Some scholars propose climate change, others suggest invasion, others propose systems failure as trade networks broke and populations were disrupted. Likely multiple factors combined. But what's undeniable is that sophisticated knowledge and capability was lost. The knowledge of maintaining Egyptian dynastic power, of governing Mycenaean territories, of sustaining trade networks, these capabilities evaporated. Civilization regression followed. Rome's fall provides another clear example. Roman engineers built structures and systems medieval Europe couldn't replicate. The knowledge of creating Roman concrete was lost. Medieval builders used inferior materials. The knowledge of maintaining aqueducts was lost. Cities that had depended on Roman systems reverted to local water sources. The knowledge of Roman military organization was lost. The sophisticated administrative systems that had held empire together disappeared. Knowledge loss was selective. Some capabilities persisted, but substantial regression occurred. The mechanisms of knowledge loss in these transitions are well understood. When master craftspeople die without training successors, knowledge dies with them. Wars and disease killed both experienced practitioners and apprentices, breaking transmission chains. When institutional structures supporting knowledge collapse, transmission systems fail. When economic systems change, craftspeople shift to different work. When cultures transform, previous knowledge systems lose value and cease to be taught. An example makes this concrete. Damascus steel represented remarkable metallurgical knowledge. Medieval smiths could create steel with properties that modern metallurgists couldn't initially replicate. But the knowledge gradually vanished. Why? The exact details are debated, but likely a combination of factors. Specific iron ore sources became unavailable. The exact process probably depended on specific knowledge maintained through master-apprentice relationships. When that relationship chain broke, the knowledge was lost. Centuries passed before modern metallurgists reverse-engineered what ancient smiths had known. This pattern repeats across history. Sophisticated knowledge exists. Civilizations transition. Knowledge loss occurs. What remains are the products surviving steel, standing monuments, ancient texts, but the methods and full understanding become unclear. Subsequent civilizations inherit fragments and mysteries. What makes this historically significant for ancient mysteries is recognition that knowledge loss doesn't require conspiracy or supernatural explanation. It happens through ordinary historical mechanisms. A civilization develops sophisticated knowledge. They build monuments and systems reflecting that knowledge. Then civilization transitions. Knowledge transfer breaks. Subsequent peoples inherit monuments they don't fully understand and gradually lose the knowledge that created them. This framework explains how ancients might have possessed capabilities we observe in their monuments without our possessing detailed knowledge of how those capabilities operated. They had the knowledge. They left the results, the monuments. The methods, if not written down, or if written in lost languages, or if maintained only through restricted training, could vanish when civilizations transitioned. We inherit the mystery and the monuments, but not complete understanding. Importantly, this transition framework doesn't require accepting exotic theories. It works with documented historical mechanisms. It explains observed evidence. It provides coherent account of how sophisticated knowledge could exist, produce undeniable results, then be substantially lost through ordinary historical processes. Investigating ancient mysteries and understanding how knowledge is lost becomes relevant to our contemporary moment. The investigation shifts from historical curiosity to present concern when we recognize how fragile knowledge systems are, how easily sophisticated understanding can be lost, and what we might need to do to preserve what matters. Consider the vulnerability of our current knowledge systems. We depend on technological infrastructure, computers, servers, networks. This infrastructure is sophisticated but fragile. Power disruption would make digital storage inaccessible. System failure would corrupt information. A sufficiently severe electromagnetic event could damage electronic systems across regions. We've built knowledge preservation systems deeply dependent on technology that could fail. Compare this to ancient approaches. Stone monuments preserve information indefinitely without power or maintenance. Oral traditions encoded in memory and story can persist across generations without technology. Mathematical principles embedded in architecture endure as long as structures stand. Ancient approaches to knowledge preservation had redundancy and resilience modern systems sometimes lack. We've also become deeply specialized. Most people understand their own field thoroughly, but know little about other domains. If specialists died without training successors, entire knowledge domains could vanish. Modern knowledge is fragmented across specialists in ways that make it vulnerable to transmission failure if institutions break down. The ancient mysteries become morally relevant when we recognize these vulnerabilities. If ancient peoples possessed sophisticated knowledge in multiple domains, maintained it across generations through careful preservation systems, and then lost substantial portions through historical transition, their experience teaches us something crucial about knowledge fragility. It should inspire us to think differently about what we preserve, how we preserve it, and what we prioritize preserving. Some knowledge is obviously important. Medical knowledge saves lives. Engineering knowledge enables technology. Agricultural knowledge enables food production. These should be preserved with redundancy and resilience. But what else matters? Mathematical principles that might only become practically relevant in distant future. Philosophical understanding. Historical knowledge? Astronomical observation? Ancient peoples preserved diverse knowledge types. Perhaps we should question whether modern society is wise in focusing so narrowly on immediately practical knowledge while allowing other understanding to atrophy. The ancient mysteries also invite reflection on what we're currently losing. With each dead language, we lose perspectives embedded in linguistic structure. With closure of libraries and archives, we lose access to historical records. With obsolescence of storage media, we lose data. With death of craftspeople who haven't trained successors, we lose practical skills. With institutional transitions, we lose knowledge repositories. We're experiencing knowledge loss in real time. Respecting ancient knowledge means taking seriously the question, what are we losing now that we won't realize is missing until centuries later? What knowledge should we prioritize preserving, even if it's not immediately profitable? What understanding is worth maintaining, even as technologies change? Ancient peoples clearly thought these questions mattered. Their monuments and the knowledge embedded in them were built to endure. The fact that we're still studying them, thousands of years later, suggests they succeeded in their preservation goals. We might learn from that approach, not by rejecting modern knowledge systems, but by augmenting them with resilience and redundancy, preserving knowledge in multiple formats, teaching practical skills alongside theory, building institutional redundancy so no single institution holds irreplaceable knowledge, thinking long-term about what knowledge deserves to endure. This investigation has traced a path from specific mysteries through evidence examination to broader synthesis. Before drawing conclusions, consolidating what has emerged is important. First, and most fundamentally, ancient peoples were sophisticated. Their engineering achievements are genuine and impressive. Their astronomical knowledge exceeded what we initially understood. Their mathematical capability was systematic and deliberate. Their water management systems functioned effectively for centuries. This sophistication is demonstrable. It requires no speculation or theory to support. The evidence itself proves it. Second, conventional explanations for how these achievements occurred contain gaps and contradictions. The timelines are mathematically problematic. The tool evidence is sparse. The construction methodology we attribute to them doesn't, when tested experimentally, consistently replicate observed results. These gaps don't prove conventional explanations are wrong, but they establish that conventional narratives are incomplete or partially incorrect. Honest acknowledgement requires recognizing these gaps, rather than maintaining false confidence. Third, alternative explanations exist that account for some evidence better than conventional approaches. Water-based construction methods, sophisticated measurement systems, acoustic technology, these aren't proven, but they're plausible given what we know of ancient capability. They explain some gaps in conventional understanding. They deserve serious investigation rather than dismissal. Fourth, knowledge loss is real and historically documented. Civilizations rise, develop sophisticated knowledge, then decline and lose that knowledge through ordinary historical mechanisms. This pattern repeats across history. Applying it to ancient mysteries helps explain how sophisticated knowledge could exist, produce undeniable results, then become partially lost. We don't need exotic explanations. Documented historical mechanisms suffice. Fifth, our historical understanding is incomplete. Archaeological evidence regularly surprises us. New discoveries revise understanding. The historical record is fragmentary, and gaps are substantial. Claiming certainty about how ancient people accomplished things despite incomplete evidence is intellectually premature. Acknowledging genuine uncertainty is more honest and more scientifically rigorous. Sixth, multiple frameworks are consistent with available evidence. Conventional emphasis on independent discovery and primitive tools explains some observations. Frameworks emphasizing diffusion through ancient trade networks explain others. Frameworks proposing previously unknown knowledge sources or advanced predecessors aren't definitively ruled out by evidence, though they're less well supported than mainstream approaches. No single framework perfectly accounts for all evidence. Seventh, ancient mysteries remain genuinely mysterious in important respects. We don't know definitively how the pyramids were constructed. We don't understand completely what knowledge systems enabled astronomical precision. We can't fully explain certain precision achievements or the timelines required. These aren't problems to dismiss with false confidence. They're genuine mysteries worthy of investigation. What emerges from synthesizing these findings is a picture of ancient peoples who were genuinely capable, who possessed sophisticated knowledge we're still understanding, who accomplished remarkable things through methods we're still working to comprehend. Not primitive ancestors needing our enlightened correction. Not impossibly advanced beings we couldn't possibly understand, but intelligent people of their time developing knowledge and capability suited to their challenges and contexts. The knowledge they possessed in certain domains exceeded what we initially understood. The monuments they built demonstrate capability that was genuine. The systems they created functioned effectively. But crucially, the complete scope of their knowledge, the full methodology of their achievements, remains partially mysterious. We see the results. We have fragments of understanding. We don't have complete knowledge. This position, respecting ancient sophistication while acknowledging genuine mystery about methods, avoids both extremes. It rejects primitive dismissal of ancients. It rejects fantastic speculation about lost superscience. It maintains intellectual rigor while acknowledging that complete understanding exceeds current evidence. It positions ancient mysteries not as solved problems or unsolvable riddles, but as genuine historical questions deserving continued investigation. From what we've discovered, certain implications follow about how to think about ancient peoples and history more broadly. These implications point toward new frameworks, more honest about what we know and don't know. The conventional framework positions history as linear progress from primitive to advanced. Ancient peoples were simple and limited. Gradually, through accumulation of knowledge and technological development, humans advanced toward modern civilization. This framework provides psychological comfort. It validates modern superiority, but the evidence doesn't fully support it. A more accurate framework recognizes that knowledge development is contingent and multidirectional. Civilizations develop sophistication in certain domains based on their priorities and challenges. They achieve genuine capability in those domains. They might simultaneously lack sophistication in other areas. When civilizations transition, they can lose previously developed capability. This isn't linear progress, it's more complex. Civilizations rise and fall. Knowledge develops and is lost. Subsequent civilizations inherit fragments and rebuild differently. Ancient peoples aren't positioned as inferior to modern people in this framework. They're positioned as different people, solving different problems with the knowledge and capabilities available to them. In some domains, construction precision, astronomical observation, water management, they achieved sophistication rivaling or exceeding what subsequent civilizations maintained. In other domains, they lacked capabilities modern civilization developed. This acknowledgement of genuine ancient sophistication is balanced with recognition that knowledge is fragile and capability can be lost. This framework has several advantages. It explains why we observe sophisticated knowledge in ancient civilizations without claiming they possessed impossible technology. It accounts for how such knowledge could be lost through ordinary historical mechanisms. It permits recognition of genuine accomplishment without requiring exotic explanations. It maintains intellectual rigor about what evidence supports and what remains mysterious. It positions ancient peoples as worthy of respect without requiring belief in false narratives about them. Such a framework becomes generative. It suggests research directions and investigative approaches. If ancient peoples developed sophisticated knowledge in specific domains, investigation can focus on understanding what that knowledge was and how it operated. If methods remain unclear, experimental archaeology can test alternative possibilities. If knowledge was lost, investigation can examine what traces might remain and what reconstruction might be possible. This framework also invites humility. If ancient peoples could lose sophisticated knowledge through historical transition, modern civilization could similarly lose knowledge if institutions failed or priorities changed. This recognition should inform how we think about knowledge preservation and cultural transmission. It should suggest that some knowledge deserves protection and redundancy beyond what market forces typically provide. The framework also permits honest acknowledgement of genuine mystery. Some ancient achievements remain incompletely understood. This isn't failure. It's accurate reflection of actual state of knowledge. Accepting that some mysteries won't be completely resolved permits focus on investigating what can be clarified rather than maintaining false certainty about what remains unclear. What distinguishes this framework from both mainstream archaeology and fringe speculation is insistence on evidence-based reasoning while maintaining openness to genuine investigation. Conventional archaeology sometimes maintains certainty beyond what evidence supports. Fringe theories sometimes accept speculation without adequate support. This framework insists on distinguishing demonstrated facts from interpretations while remaining open to investigating alternative frameworks when evidence permits. It also acknowledges that the most honest position regarding ancient mysteries is one of intellectual humility combined with rigorous investigation. We should simultaneously maintain high standards for what we claim to know, remain open to genuine investigation of alternatives, and accept that some questions might not be answered definitively with current evidence. This isn't weakness, it's intellectual maturity. This investigation has raised far more questions than answered. Rather than providing definitive solutions to ancient mysteries, it has clarified what we know, what remains uncertain, and what deserves investigation. What methods actually moved and positioned the massive stones at ancient sites? This is fundamentally unanswered. Conventional explanations are problematic. Alternative methods remain plausible, but unproven. Experimental archaeology, systematically testing different approaches, could clarify possibilities. Geological analysis of stone surfaces might reveal tool marks indicating specific methods. Archaeological investigation of quarry sites and transportation routes might reveal evidence of methods used. This isn't frivolous speculation. It's serious investigation that could meaningfully advance understanding. What knowledge systems enabled the astronomical precision ancients demonstrated? We know they possessed genuine astronomical knowledge. We don't know completely what observation techniques, what measurement systems, or what mathematical frameworks they employed. Historical analysis of surviving texts combined with experimental investigation of potential observation methods, could clarify this. Understanding ancient astronomy better would illuminate their broader knowledge systems. What role did water management play in ancient construction? This avenue remains largely uninvestigated by mainstream archaeology. Experimental investigation of water-based construction methods, examination of ancient Egyptian texts for references to water in construction, geological analysis of construction sites for evidence of water systems, these could clarify whether water technology played a role in ancient engineering. What ancient texts, now lost or surviving but untranslated, might contain encoded technical knowledge? Ongoing translation efforts combined with investigation for technical information encoded in mythological narratives could uncover knowledge we've dismissed as purely spiritual or entertainment. What materials and tools did ancients possess that we've underestimated? Metallurgical analysis of surviving ancient tools, experimental testing of supposedly primitive materials to determine what they could actually accomplish, investigation of tool marks on monuments, these could reveal what capabilities ancients actually possessed. What role did restricted knowledge systems and priestly classes play in maintaining technological knowledge? Historical and textual analysis, combined with archaeological investigation of temple and ceremonial sites, could clarify whether restricted knowledge systems maintained information not available in general population. These questions aren't frivolous. They're genuine research directions that could meaningfully advance understanding if pursued with rigor. What prevents such investigation isn't scientific impossibility, it's institutional prioritization. Mainstream archaeology has established frameworks that discourage alternative investigation. Research funding flows toward confirming existing paradigms. Academic career advancement favors work-fitting established narratives. This institutional bias prevents systematic investigation of genuinely interesting questions. Yet the questions remain worthy of investigation. Some might confirm conventional understanding more solidly if properly tested. Others might reveal new possibilities. Either way, investigation would advance understanding. The fact that such investigation isn't systematically pursued suggests institutional resistance rather than scientific evidence that investigation wouldn't be productive. This is worth acknowledging. It's not conspiracy. It's how institutions naturally protect themselves. But it means rigorous investigation of ancient mysteries remains incomplete. This investigation into ancient mysteries has been, in some sense, a mirror. Looking at ancient peoples and their achievements, we've seen reflections of ourselves, of how we approach knowledge, of what we believe, of the certainties we maintain, of the questions we refuse to ask. The ancient mysteries exist partly because we've constructed frameworks of understanding, and then defended those frameworks rather than genuinely investigating challenges to them. We've created narratives about how history unfolded, and we've become invested in those narratives. When evidence emerges that contradicts the narratives, we don't revise the narratives. We reinterpret the evidence. This isn't unique to archaeology. This is how human thinking works. We develop beliefs. We defend them. We resist revision even when contradictory evidence accumulates. Understanding this tendency in ourselves is crucial. It doesn't require cynicism about science or expertise. Scientists are intelligent and committed to understanding reality accurately. But they're also human. They operate within institutions. They have careers to maintain. They have beliefs they've invested in defending. These human realities don't negate the value of scientific investigation. They simply establish that science operates within context of human limitation and bias. The ancient mysteries invite us to ask, where else are we maintaining narratives despite contradictory evidence? Where are we defending established frameworks rather than genuinely investigating challenges? Where are we dismissing possibilities without rigorous investigation, simply because they challenge established thinking? These are uncomfortable questions. But they're worth asking because they apply broadly to how we approach knowledge and understanding. The mysteries also teach us something about the fragility of knowledge itself. Ancient peoples possessed sophisticated understanding in certain domains. That knowledge produced undeniable results. Yet substantial portions of it were lost. We're still trying to recover and understand what they knew. This should humble us. If ancient knowledge could be lost, modern knowledge is equally vulnerable. If sophisticated understanding could vanish through historical transition, Our sophisticated knowledge could similarly disappear if institutions failed or priorities shifted. This recognition carries moral weight. Knowledge matters. Preserving knowledge matters. Transmitting knowledge to subsequent generations matters. Ancient peoples invested enormous effort in building monuments that would endure. They developed systems for preserving knowledge. They created redundant transmission methods, oral tradition, written record, architectural encoding. They clearly understood that knowledge is precious and fragile. We live in an era of information abundance. We have more data than any previous era, yet we're simultaneously vulnerable. Digital information depends on technology that could fail. Specialized knowledge is fragmented across experts in ways that make transmission difficult. If institutions failed, much of our sophisticated knowledge would become inaccessible. This paradox, abundant information but fragile knowledge systems, deserves attention. The ancient mysteries also reveal something about human capability and our tendency to underestimate it. For centuries we assumed ancients were primitive and limited. Yet evidence of their sophistication keeps accumulating. They were intelligent people capable of remarkable achievement. This recognition should inspire respect for human capability generally. It should also inspire humility if we've underestimated ancient peoples. What else might we be underestimating? What capabilities do we dismiss in populations we've stereotyped? What possibilities do we reject without adequate investigation? Finally, the mysteries teach us that genuine wonder is valuable. Not credulity or gullibility, but authentic curiosity about what we don't understand. Ancient peoples faced their own mysteries. They looked upward at stars. They examined stone. They studied water. They engaged with what they didn't understand through careful observation and thought. That approach, meeting mystery with respect and investigation, remains valuable. It's how understanding deepens. It's how we grow. Investigating ancient mysteries illuminates an uncomfortable truth. We have responsibility regarding knowledge that extends beyond our immediate lifetimes. Ancient peoples understood this. They built things designed to last millennia. They preserved knowledge deliberately. They created redundancy, ensuring crucial information wouldn't be lost. They made choices, thinking about future generations. We face similar choices. How we approach knowledge preservation and transmission will determine what future generations inherit. If we treat knowledge carelessly, prioritize immediate profit over preservation, fail to maintain diversity in how we store information, then we risk repeating ancient patterns, achieving sophistication, then losing it through transition. What would it mean to take this responsibility seriously? First, it would mean committing to genuine investigation of questions that matter, even if investigation challenges established frameworks. We should welcome genuine challenge to our understanding, rather than defending frameworks reflexively. This doesn't mean abandoning skepticism. Rigorous investigation requires skepticism. But skepticism should be directed toward all claims equally, not reserved for claims that challenge established paradigms. Second, it would mean funding and supporting research into mysteries and questions, even if answers aren't immediately profitable. Some knowledge matters for understanding human history and capability, even if it doesn't generate economic return. Universities and research institutions exist partly to investigate such questions. We should protect and support that function, rather than pressuring research toward immediately profitable applications. Third, it would mean building redundancy into knowledge preservation systems. We shouldn't depend entirely on digital storage for crucial knowledge. We should preserve information in multiple formats, some digital, some physical, some in human knowledge and skill. We should maintain communities where practical knowledge is actively used and transmitted. We should teach understanding alongside technology. We should recognize that some knowledge is valuable to maintain, even if it's not immediately practical. Fourth, it would mean supporting interdisciplinary collaboration in investigating complex questions. Ancient mysteries often remain unsolved, partly because they're examined through single disciplinary lenses. Engineers, archaeologists, geologists, mathematicians, collaborating genuinely could generate insights none would achieve alone. Creating institutional structures supporting such collaboration would be valuable. Fifth, it would mean intellectual humility about what we know and don't know. We should distinguish confidently between what evidence supports and what remains uncertain. We should acknowledge genuine gaps in understanding rather than maintaining false certainty. We should remain open to revision as evidence accumulates. This intellectual humility, while uncomfortable, is more scientifically rigorous than defensive confidence. Sixth, it would mean recognizing that ancient peoples deserve respect. They were intelligent. They solved problems creatively. They achieved genuine sophistication. We can respect this while acknowledging we don't fully understand their methods. We can learn from their approach to knowledge preservation without naively imagining we should simply copy ancient methods. We can recognize that their experience developing sophisticated knowledge, then losing portions of it, teaches us something about knowledge fragility we should take seriously. The responsibility extends to recognizing that how we treat this knowledge reflects what we value. If we dismiss ancient mysteries as unsolvable riddles, we devalue understanding. If we maintain false certainty about how ancient monuments were built, we avoid genuine investigation. If we treat ancient peoples as primitive ancestors needing our enlightened correction, we fail to learn from them. If we take mysteries seriously, investigate genuinely, remain open to what we might discover, and respect what ancient peoples accomplished, we honor both them and the importance of knowledge itself. These aren't abstract ethical considerations. They have practical implications. They suggest how we should fund research, how we should approach historical investigation, how we should preserve knowledge for future generations, how we should respect the achievements of those who came before us. The ancient mysteries, approached seriously, become invitations to think differently about our responsibilities regarding knowledge. Every investigation of history ultimately involves choosing a narrative. We select which evidence to emphasize, which patterns to highlight, which framework to use for interpreting ambiguous information. These choices shape what story we tell about ancient peoples and what that story implies about human nature and history itself. We could tell a story where ancient peoples were primitive and gradually advanced toward our superiority. This narrative is comforting. It validates modern civilization. It suggests progress. It presents history as improvement. Much of conventional archaeology implicitly tells this story, but the evidence only partially supports it. Ancient peoples were sophisticated in important ways. They achieved genuine accomplishments. They weren't primitive ancestors climbing toward enlightenment. We could tell a story where ancient peoples possessed impossible technology far exceeding ours. This narrative is romantic. It imagines a golden age more advanced than present. It appeals to dissatisfaction with modernity. But this story requires speculating beyond evidence. It invents capabilities not clearly supported by archaeology. It transforms mystery into certainty without adequate justification. We could tell a story where ancient peoples were intelligent, capable beings who developed sophisticated knowledge in certain domains suited to their challenges and contexts. They achieved genuine accomplishment. They built things designed to last millennia. They created knowledge preservation systems. They possessed understanding we're still working to recover. But they also lost knowledge through historical transition. Methods we don't completely understand enabled their achievements. Some mysteries remain despite investigation. This story requires living with genuine uncertainty rather than claiming false confidence. But it's more honest. It respects ancient peoples without romanticizing them. It acknowledges both what they achieved and what remains mysterious. The story we choose to tell reflects what we believe about knowledge, capability, and humanity itself. If we dismiss ancients as primitive, we diminish human capability. If we imagine them as impossibly advanced, we create impossible standards and distance ourselves from them. If we recognize them as intelligent people different from us, capable of genuine achievement despite using knowledge we don't fully understand, we honor both them and ourselves. This choice matters because the story we tell about the past influences how we see ourselves and future possibilities. If history is simple progress from primitive to advanced, we should expect future advancement to continue similar patterns. If history is more complex, civilizations rising and falling, knowledge developing and being lost, different peoples prioritizing different knowledge domains, then we should be more cautious about assuming progress is inevitable. We should be more concerned about preserving knowledge. We should be humbler about our own certainty regarding what matters and what will endure. The ancient mysteries ultimately are invitations. Invitations to think differently about history. Invitations to respect human capability across time. Invitations to investigate seriously what we don't understand. Invitations to preserve knowledge we might otherwise lose. Invitations to choose humble curiosity over confident certainty. Ancient peoples built monuments and preserved knowledge, believing future generations would care about understanding. They were right. We do care. The question is, what we do with that care, whether we investigate genuinely or maintain defensive certainty, whether we preserve knowledge or allow it to slip away, whether we respect the past or dismiss it as primitive. The choice, ultimately, is ours. And that choice reveals what we believe matters. There's a particular kind of satisfaction that comes not from answers, but from asking better questions. Throughout this investigation, we've traced mysteries across continents and centuries. We've examined evidence. We've explored possibilities. We've tested our assumptions about history and human capability. What we've discovered is that ancient peoples were genuine. Their achievements were real. Their knowledge was sophisticated. But how they accomplished what they did remains partially mysterious. That mystery isn't failure. It's actually valuable. A world where everything is explained and solved is diminished. A world containing genuine mystery where intelligent investigation reveals partial understanding but authentic gaps remain is richer. The ancient peoples faced their own mysteries. They looked at stone and stars and water and the challenges before them. They engaged seriously with problems. They developed knowledge. They built things designed to endure. They created systems meant to preserve understanding across generations. They understood that mystery is part of existence, and that responding to mystery with curiosity and care is how human beings grow. We're in a position they couldn't imagine. We have technologies they couldn't conceive. We've accumulated knowledge across generations. We've built institutions dedicated to understanding. Yet we've also inherited their mysteries. We see their monuments. We study their knowledge. We ask how they accomplished what they did. Maybe the real gift they've left us isn't specific answers to how they built their monuments. Maybe it's the invitation to think, to question, to investigate, to remain open to possibilities we haven't fully considered. Maybe it's the reminder that knowledge is precious and fragile. Maybe it's the model of people committed to understanding despite operating within limitation and mystery. The ancient mysteries remain. Some might be solved through continued investigation. Others might always contain uncertainty. But in engaging with them, in taking them seriously, in respecting the intelligence and capability of ancient peoples while acknowledging what we don't understand, we honor both them and something important about the human search for understanding. The investigation continues, not just in this documentary or any single inquiry, but in the ongoing human commitment to understanding our past and ourselves. That commitment, that curiosity, that willingness to question and investigate, perhaps that's the real ancient inheritance. And perhaps continuing that work is how we honor what they achieved and what they still have to teach us.